Welcome back to QHSE Talks. So I want you to imagine an aviation engineer, right? Back in the late 1940s.
Okay, setting the scene. I like it.
Yeah, so they are spending millions of dollars to design this absolute state-of-the-art fighter jet cockpit, and they measure thousands of pilots.
Right, getting all the data.
Exactly. They find the exact mathematical average for, height, arm length, leg length, and then they build this beautifully fixed, rigid cockpit that is perfectly sized for that one singular average pilot.
And let me guess, it was a total disaster.
An absolute catastrophe. Almost every single pilot who climbed into that plane, they struggled to reach the flight stick, or they couldn't fully push down the rudder pedals, or like their helmet was literally jammed up into the canopy.
Because the average person doesn't actually exist.
Right. By designing for the exact average, they essentially designed a workstation that fit literally no one. It led to catastrophic errors in the sky. And, that historical failure is exactly why modern safety professionals do not guess when it comes to the human body.
Well, yeah, and that paradigm shift, that is the entire foundation of our field today.
Yeah.
Because for decades, the prevailing industrial philosophy was Taylorism.
Oh, right. The old efficiency model.
Exactly. The idea that you build the most efficient machine possible, and then you just find a human being who is, malleable enough to operate it, regardless of the physical contortions required.
You just force the person to fit the job.
Right. But ergonomics completely inverts that model. The science demands that we design the machine, the workstation, the entire manufacturing process around the unchangeable biological realities of the human body.
And that inversion, that is our mission today. Because if you are a safety professional preparing to conquer the ASPExam, specifically Domain 3, Topic 7, you are in the exact right place.
It's a heavy topic for sure.
It is, yeah. Today's QHSE Talks is a laser-focused session. We're unpacking exactly how you identify and deploy ergonomic, qualitative, and quantitative analysis methods.
So we're talking about the distinct tools, the statistical metrics, the biomechanical philosophies.
All of it. The stuff that lets you step onto a factory floor or, into a distribution center or even just a corporate office and accurately assess the physical toll that the environment is taking on the workforce.
And for you listening, this isn't just about memorizing acronyms to pass a test. This is an essential, foundational skill for actually performing your safety duties in the real world.
Absolutely. Because as the saying goes, you can't fix what you can't measure.
Right. And in occupational health, measuring that human-machine interface, well, that's the difference between a thriving workforce and a staggering workers' comp premium.
Yeah, a premium that will make your CFO pass out.
Yeah.
So to map all of this out for you, we are pulling from a really heavy stack of curated sources today. We've got the CSP and ASP exam study guides, the official BCSP blueprint PDFs.
Always got to have the blueprints.
Always. Plus practice questions from Bowen EHS and the Safety Professionals Reference and Study Guide. Now, I do want to set some parameters for today's QHSE Talks, just to keep us on track.
Good idea. What are the boundaries?
Well, while the NIOSH lifting equation is a major part of Domain 3, Topic 7, we are actually going to spend a bit less time on it today.
Right, because we've covered its complex multipliers extensively in previous sessions.
Exactly. We will hit the core metrics you need for this specific topic, but our primary focus is going to be on the broader spectrum of assessment methods. So, okay, let's unpack this. How do we actually measure the physical toll a job takes on a human being? Because for a long time, ergonomics felt, incredibly vague.
Oh, totally. It used to literally just be walking up to a worker and asking, hey, does your shoulder hurt today?
Right. And that's not exactly scientific. But the sources outline this fundamental division in how we evaluate work sites. We have qualitative versus quantitative risk assessments. So why do safety professionals need both of these methodologies in the toolkit?
Because they serve entirely different functional purposes, right? Like in a risk management system, you need both. Think of the qualitative assessment as the triage nurse in an emergency room.
Okay, I like that analogy.
And then the quantitative assessment, that's the orthopedic surgeon.
Okay. The triage nurse and the surgeon.
Right. So the triage nurse, they don't need a high-tech scan to know a patient is in distress, right? They use structured observation. They ask specific questions about pain levels. They look for immediate red flags.
Just to figure out who needs care first.
Exactly. It's about prioritization. And in industrial hygiene, qualitative methods act as that vital first line of defense. We're utilizing tools like structured hazard identification checklists Or observational surveys done by trained ergonomists.
And subjective employee symptom reports, right?
Yeah.
That's mentioned a lot in the guides.
Yeah, subjective employee ratings are huge for evaluating physical and mental fatigue.
But wait, let me push back on that for a second, because I can hear some of you listening raising an eyebrow right now. If qualitative assessments rely so heavily on how someone, feels, isn't that a somewhat dangerous foundation for a safety professional to rely on?
Well, how so?
I mean, feelings aren't objective facts, right?
Yeah.
An employee might say a task is incredibly fatiguing simply because they find it boring. Or conversely, they might underreport severe pain because they're afraid of losing overtime hours.
Oh, that happens all the time, the psychological noise.
Exactly. So how do we filter out that psychological noise to find the actual ergonomic hazard? Qualitative feels like a smoke detector, just tells you there's a problem, but it doesn't give you the exact temperature of the fire.
That's a great way to look at it. But the key word in the sources regarding qualitative data is formalized. It is a formalized approach.
Okay, so it's not just a casual chat.
Right. Qualitative assessment isn't just walking the shop floor and shooting the breeze. We use highly validated structured tools. Take something like the Nordic Musculoskeletal questionnaire or a formalized symptom body map.
Or they actually point to the body part on a drawing.
Yes. We aren't just asking, are you tired? We're asking the worker to pinpoint on a diagram the exact location of the discomfort. We ask them to rate the frequency on a standardized scale and describe the nature of the pain. Is it a dull ache, a sharp stab, a tingling sensation?
Also, it's highly specific.
Very specific. And when you take that formalized tool and you deploy it across an entire department of, say, 200 people, that individual psychological noise you mentioned, it begins to wash out.
Because statistical patterns start to emerge.
Exactly.
Yeah.
If 75% of the workers on a specific packaging line report sharp tingling pain in their right wrist within 2 hours of their shift, well, that is no longer a subjective feeling. That is a localized, systemic, ergonomic hazard demanding intervention.
Wow, yeah. The aggregate data reveals the truth. The triage nurse spots that the entire packaging line is in trouble.
Right. And beyond just symptom surveys, qualitative methods include observational checklists. A safety professional might walk the floor looking for 4 specific risk factors: high force, high repetition, awkward postures, and contact stress.
Contact stress, like resting your wrist on a hard desk edge.
Yeah. Or if you see a worker using their hand as a hammer to knock a component into place, you don't need a biomechanical computer model to tell you that's contact stress.
The checklist flags it immediately.
Right. The overarching purpose of qualitative measures is to establish a benchmark and prioritize where you spend your limited time and resources. When you walk into a facility with 5,000 workstations, you can't immediately run a mathematical model on every single one. You sweep the floor with qualitative tools to find the bleeding.
Which brings us to the surgeon in your analogy. We've triaged the problem. We know the packaging line is destroying wrists. Now we need the precise measurements to actually fix the machine.
Yes. And that is where quantitative methods come in. We abandon subjective reporting and move entirely into instrumentation, objective data collection, and hard calculation.
So what are we actually measuring here?
Well, we're talking about things like using electromyography or EMG to measure the exact electrical activity in a muscle group so we can see how fast it is fatiguing.
Oh, wow. Actually measuring the electrical impulses.
Yeah. We're talking about heart rate monitors measuring physiological strain over an 8-hour shift to calculate metabolic load, or applying biomechanical models that measure the exact compressive and shear forces acting on the spine during a lift.
So if the qualitative checklist tells us where to look, the quantitative tools give us the exact numbers we need to re-engineer the workstation.
Exactly. You might discover through quantitative analysis that inserting a particular component requires 22 pounds of pinch force, but based on biomechanical data, human tendons in that specific awkward posture begin to micro-tear at 12 pounds.
So you have proof that the job is physically impossible to do safely.
Right. And that exact hard number is what you take to the engineering department or the CFO to justify the capital expenditure for, say, an automated insertion tool.
Because you can't just walk into a boardroom and say, the worker's hands hurt, we need $100,000 for new equipment.
They'll laugh you out of the room. But if you walk in and say, the mechanical demand of this task exceeds the physiological capability of 80% of our workforce, which mathematically guarantees a spike in musculoskeletal disorders and medical payouts, well, now they're listening. Quantitative data provides the financial and engineering justification.
But, to know if a task exceeds human capability, we first have to understand the mathematical boundaries of the human body itself, right? Like we have to know what those physical capabilities actually are, which leads us perfectly into the science of anthropometry.
Yes, anthropometry. If we connect this to the bigger picture, this is the core of everything we do.
So let's define it for the listener. What exactly is it?
Well, the word derives from the Greek anthropos, meaning human, and metron, meaning measure. It is the literal measurement of the human body to ensure the machine is designed to fit the individual.
Right. And the exam blueprints and our sources, they break this down into two distinct classes of data: static data and dynamic or functional data.
That's right. So static anthropometry is measured when the human body is in a fixed, rigid position. You are just capturing the sheer dimensions of the body's segments.
Like just standing there with a tape measure.
Exactly. Overall, standing height, sitting height, the length of the forearm from the elbow to the fingertips, the breadth of the shoulders, and popliteal height.
Popliteal height. That is the distance from the floor to the crease behind the knee when seated, right?
Yes, exactly.
It is a perfect example of why this matters so much in like office ergonomics. Because if you don't use static anthropometric data to design a chair and the seat pan is too high relative to a worker's popliteal height, their feet dangle.
And that is a huge problem.
Yeah, all the weight of their legs pulls down, and the front edge of the chair presses directly into the back of their knees. It cuts off circulation and compresses nerves.
Right. And conversely, if the seat pan is too long, meaning the depth of the chair exceeds the length of their upper leg, they can't sit all the way back against the lumbar support without the edge of the chair biting into their calves.
Oh, so they're forced to sort of perch on the front edge of the seat.
Exactly, which completely destroys their lower back posture.
Yeah.
So static data dictates the physical boundaries of the workspace. It determines how high a desk should be, how much clearance is needed under a console so a worker's knees don't smash into the drawers, how wide a doorway needs to be.
But static data is really just the architecture of the body at rest. And a factory floor is not a museum of statues, right? People move. They work. That's where the second-class dynamic or functional anthropometric data takes over.
Right. Functional data measures the body in motion, performing specific tasks. And the most critical concept here is the reach envelope.
The reach envelope, explain that for us.
When you sit at a desk or stand at a conveyor belt, there is a three-dimensional semicircle around you where you can comfortably reach items without having to bend your spine or overextend your shoulder. Functional data maps those zones.
Okay, so it's mapping where things should go.
Exactly. We measure the primary reach zone, which is where your elbows are bent and resting naturally near your sides. That's where the most frequently used tools should be placed.
Makes sense.
Then we measure the secondary reach zone. That's where your arms are fully extended, but your back remains straight. Anything beyond that secondary zone requires leaning, which introduces severe biomechanical stress if done repetitively.
And functional data also measures the actual force the body can generate in different directions, right? Because your grip strength when your wrist is perfectly straight is vastly different from your grip strength when your wrist is bent at like a 45-degree angle.
Vastly different. The biomechanics actually dictate that when the wrist deviates from a neutral posture, the tendons literally have to bend around the bones and ligaments to pull the fingers closed.
Ouch. That sounds like it creates a lot of friction.
Immense internal friction. Functional anthropometry measures exactly how much force is lost in those awkward postures. It tells us what the body can actually do within the physical space we designed using the static data.
And this brings us back to that fighter pilot problem we opened with. How do we apply all these static and functional measurements to an actual population of workers? You know, the sources introduce a fascinating statistical concept that is heavily tested on the ASP exam.
Ah, yes, the percentile principle, designing for the 5th, 50th, and 95th percentiles.
Right. Break down what that actually means in practice.
Well, when you measure a physical trait across a massive population, say the standing height of 10,000 manufacturing workers, that data will naturally distribute itself into a bell curve.
Sure, standard distribution.
Right. The 50th percentile is the dead center, the exact statistical average.
Yeah.
But the 5th percentile represents the smaller end of the spectrum. 95% of the population is statistically larger than the 5th percentile value.
Okay, and the 95th.
The 95th percentile represents the larger end. 95% of the population is smaller than this value.
So going back to the car seat analogy, if you only design a static seat for the 50th percentile, the exact average, You are actively excluding the extremes.
You're making the workstation uncomfortable and potentially hazardous for half your workforce.
Right. A driver in the 5th percentile can't reach the gas pedal, and a driver in the 95th percentile has their head pressed into the roof.
Which is why the cardinal rule of ergonomics is to design for adjustability, using the 5th and 95th percentiles to establish the required range.
Adjustability is key.
Always. A standing workbench must be adjustable enough to go low enough for the 5th percentile worker so they don't have to constantly elevate their shoulders and fatigue their trapezius muscles. And it must go high enough for the 95th percentile worker so they don't have to continuously flex their lumbar spine forward.
Right. If a desk is too low, the neck and back flex. If it's too high, the shoulders elevate. But there is a very specific rule of thumb for the exam regarding when to use which percentile for fixed unadjustable elements.
Yes, this is crucial for the exam.
If you are designed for clearance, like the height of an emergency exit door, or the legroom under a fixed console, you design for the 95th percentile.
Right, you design for the largest person, ensuring that everyone smaller will easily fit.
But if you're designing for reach, like how far away the emergency stop button on a machine should be, you design for the 5th percentile. You place it close enough for the smallest person with the shortest arms to reach it, which guarantees that everyone larger can also reach it.
Clearance is for the 95th, reach is for the 5th. Keeping that specific distinction in mind will absolutely save you points on the test. And frankly, it prevents fundamental design flaws on the shop floor.
Definitely. Now, I want to take these concepts of measurement and motion and look at a specific practice question from the Bowen EHS CSP question bank.
Lay it on me.
The question asks about an instrument called a goniometer. What is it, and how is it used in ergonomic analysis?
Ah, the goniometer. This is the bridge between qualitative observation and quantitative data for joint movement.
Okay, how so?
Well, when we talk about functional anthropometry, we need to know exactly how far a joint is bending. A goniometer is essentially a highly precise, specialized protractor. It's used for three-dimensionally measuring the full range of motion of human joints during a work activity.
Specifically measuring the angles associated with joints like knees, elbows, wrists, and ankles, right?
Exactly. Physically, it usually looks like a dial with two long arms extending from it. You place the center fulcrum directly over the joint, say, the wrist. You align one arm of the goniometer along the forearm and the other arm along the hand.
And then as the worker performs a task.
Right, like twisting a screwdriver or pulling a lever, the goniometer tracks the exact angle the wrist moves through.
And that data is invaluable because human joints are not simple hinges. They move in multiple planes.
Exactly. A goniometer allows a safety professional to measure flexion and extension, which is bending the wrist forward and backward. It measures pronation and supination, which is rotating the forearm palm down or palm up.
And critically for the wrist, it measures radial and ulnar deviation.
Yes, bending the wrist side to side toward the thumb or toward the pinky finger.
Right. And ulnar deviation is a massive culprit in musculoskeletal disorders, isn't it?
Oh, absolutely. If an assembly worker is constantly bending their wrist sideways toward their pinky to snap apart into place, the tendons connecting their forearm muscles to their fingers are just being dragged violently back and forth across the carpal bones.
The goniometer lets you actually quantify that violence. Because a qualitative observation just tells you, the worker is bending their wrist awkwardly. But the goniometer gives you the quantitative hard data.
Right. It says the worker is forcing their wrist into 35 degrees of ulnar deviation against 10 pounds of resistance 400 times an hour.
Wow. And then you compare those exact measurements against established physiological limits.
And you instantly know the probability of that worker developing de Quervain's tenosynovitis or carpal tunnel syndrome.
But, I have to point out the limitation there. Attaching physical goniometers to workers is incredibly accurate, but it is highly intrusive.
Oh, it's a logistical nightmare.
Right. You have to stop production, tape, or strap this instrument to a worker's arm and have them awkwardly try to work while you hover over them reading a dial. What if you have a massive facility and you need to conduct ergonomic risk assessments on 50 entirely different complex tasks in a single week?
You can't strap a goniometer to every joint on every worker. It's just not feasible.
No, it's not. And that's the exact logistical bottleneck that plagued safety professionals for decades. We needed tools that were faster, less intrusive, but still yielded reliable quantitative baseline numbers, which is where the ASP blueprint directs us toward tech-assisted rapid assessments.
Specifically RULA and REBA.
Right. Here's where it gets really interesting, because we are bringing video and software into the safety professionals toolkit. RULA stands for Rapid Upper Limb Assessment, and REBA stands for Rapid Entire Body Assessment.
We're essentially moving from the era of hand-drawn animation into the era of motion capture technology.
Yes. Let's dive deep into RUL first, Rapid Upper Limb Assessment. As the name implies, this tool is highly specialized.
It is. RULA was developed in the early 90s specifically to evaluate the biomechanical and postural load requirements of job tasks that place severe demands on the neck, trunk, and upper extremities.
So it targets upper extremity musculoskeletal disorders, or MSDs.
Exactly. It is the go-to rapid assessment tool for sedentary tasks. If you are evaluating office workers at a computer, electronics assemblers sitting at a microscope, or, workers doing fine motor work at a fixed bench, RULA is the weapon of choice.
Because it assumes the legs are largely stationary and focuses intensely on what the upper kinetic chain is doing.
Right. To understand how RULA works, you have to understand its step-by-step scoring breakdown. The tool literally divides the body into two groups. Group A analyzes the arms and wrists. Group B analyzes the neck, trunk, and legs.
Let's walk through how a safety professional actually generates a RULA score. Say we have that electronics assembly worker sitting at a bench soldering tiny wires.
Okay, good example. So for Group A, the first thing we look at is the upper arm posture. We measure the angle of flexion or extension at the shoulder. If their upper arm is hanging naturally at their side, that's a baseline score of 1.
Okay, that makes sense.
But if they have to reach forward, raising their elbow away from their torso between 45 and 90 degrees to reach the soldering iron, the score increases. If their shoulder is elevated, meaning they are shrugging because the desk is too high, we add another point.
And if their arm's abducted, meaning their elbow is flaring out to the side,
we add another point.
Wow, so the score just compounds. And we do the same precise breakdown for the lower arm and the wrist, right? Like, are they bending the elbow past 100 degrees? Is the wrist twisting?
Exactly. We take all those individual posture scores for Group A and put them into a specific matrix to get a single number. Then we do the exact same thing for Group B, the neck, trunk, and legs.
So is the neck twisting? Is the trunk bending forward more than 20 degrees? Are the legs fully supported by a footrest? Or are they dangling awkwardly?
Right. And once you have the postural scores for Group A and Group B, RULA requires you to account for two more critical factors: force and muscle use.
Because it doesn't just matter what posture you are in, it matters how long you hold it and what you are holding.
Exactly. If the posture is largely static, meaning it is held for longer than 1 minute, or if the action is repeated more than 4 times per minute, you add a muscle use score. Then you look at the load. Are they holding a lightweight microchip or a heavy pneumatic drill?
The heavier the load, or the greater the force required, the higher the force score you add.
Yes. Finally, all these numbers feed into a grand score table, generating a single final number between 1 and 7.
Now, our source text provides a very specific example of a RULA analysis output. In the scenario, the video analysis outputted an overall medium MSD risk with a score of 6. And the breakdown showed that this score of 6 was heavily driven by high risk, specifically in the upper arm.
Right, and understanding that 1 to 7 scale is essential. A score of 1 or 2 means the posture is acceptable if it's not maintained or repeated for long periods.
Okay, and a 3 or 4?
A 3 or 4 indicates that further investigation is needed and changes may be required. A score of 5 or 6, like in our source example, means investigation and changes are required soon.
And a 7?
A 7 means investigate and implement changes immediately. So a 6 is a clear mandate to intervene.
So what do we do with that data? So what? Right. Because the RULA matrix shows you exactly how the score was built, it acts as a diagnostic blueprint.
It does.
If the grand score is a 6, and I can see the points skyrocketed specifically in the upper arm section, I don't have to guess how to fix the workstation. The data is telling me the worker's reaching too far or too high.
So you implement controls. You shorten or lower the reach for the assembly parts. You bring the parts bin closer or lower the bench height. The upper arm score drops, and the overall RULA score drops into the safe zone.
It's brilliantly simple. But historically, doing this required a safety professional to stand on the floor with a clipboard and paper charts, furiously trying to estimate angles by eye while the worker moved.
Very time-consuming,
Yeah.
and very prone to human error.
Right. But modern professionals use software. The sources specifically note platforms like Tumeke, Velocity EHS, or ErgoPlus.
This is where artificial intelligence and computer vision enter the toolkit. Today, you take your smartphone or tablet, you record a short video of the worker, usually from a sagittal view, meaning from the side, so you can see the flexion and extension, and you just upload it.
And the software takes over.
Yeah. The algorithms utilized by these platforms are built on advanced pose estimation models. It analyzes the video frame by frame, identifies key anatomical landmarks, and digitally overlays a wireframe skeleton onto the worker.
And it automatically calculates the exact angles of every joint.
Thousands of times a second, applying the entire RULA scoring matrix instantaneously.
It is staggering technology. But RULA, by definition, is focused on the upper body, primarily for sedentary tasks. What happens when the job isn't seated? What if you were evaluating a warehouse worker lifting heavy boxes or a healthcare worker transferring a patient?
Well, you can't use RULA for that. That is where you deploy REBA, the Rapid Entire Body Assessment.
Okay, so how does REBA differ fundamentally from RULA?
Well, while RULA handles the upper extremity, REBA expands the scope to evaluate the entire body's risk for MSDs. It looks at the whole kinetic chain.
Because it's designed for dynamic, unpredictable work environments.
Exactly. First, the leg score in REBA is significantly more complex and heavily weighted. In RULA, the legs are mostly an afterthought because the worker is sitting. But in REBA, the algorithm evaluates exactly how the legs are bearing weight.
Like, are they standing evenly on both feet, or is their weight shifted awkwardly?
Right. Are their knees bent? Are they walking or moving while bearing a load? The lower body provides the foundation for power generation in dynamic tasks, and REBA accounts for the massive strain placed on the knees and hips.
So in addition to the neck, trunk, and arms, REBA heavily analyzes the leg score. It also looks at the risk score differently, doesn't it?
It does. And REBA introduces a critical new metric called the coupling score.
Coupling. Explain that.
Coupling evaluates how well the worker can actually grip the object they are handling. If a warehouse worker is lifting a sturdy box with well-designed handles, the coupling is good, and no penalty points are added.
But what if they are lifting like a slick, heavy sack of fertilizer with no handles? Or a patient's loose clothing?
Then the coupling is poor or unacceptable, and the REBA score increases significantly. Because poor coupling forces the worker to squeeze harder, which fatigues the forearm muscles faster and severely limits the total weight they can safely lift.
Got it. And the scoring scale for REBA is entirely different from RULA, right? Our sources give us an example where a REBA video analysis resulted in a high MSD risk with a score of 9.
Yes. REBA operates on a scale of 1 to 15. A score of 1 means negligible risk. 2 to 3 is low risk. 4 to 7 is medium risk. 8 to 10 is high risk, calling for prompt investigation, and 11 to 15 is very high risk, requiring immediate emergency intervention.
So a score of 9.
A score of 9 means the task involves full body postures that are statistically guaranteed to result in a severe injury, like a herniated disc, if the task is not modified promptly.
Okay, I love how fast and accessible this software makes the process. But let me push back a little here. We have to look critically at the limitations of this technology.
Oh, absolutely. It's not a magic bullet.
Right. Is simply uploading a 2D video into a software program enough to capture the true 3D physical strain on a worker, tying it back to the need for 3D measurements like those taken by the goniometer we talked about earlier.
You've hit on exactly why ergonomists don't just blindly trust 2D video. When we talked about the goniometer, we were measuring true physical three-dimensional reality. A RULA or REBA software program running on a tablet is attempting to extract 3D joint angles from a flat 2D video.
And occlusion is a massive enemy there.
Huge. If the worker's body turns slightly, their torso might block the camera's view of their left arm. How can the AI calculate a wrist angle it can't even see?
It can't. Or worse, it just extrapolates and guesses incorrectly.
Exactly. And beyond occlusion, you have severe parallax errors. If the camera isn't positioned perfectly perpendicular to the plane of motion, the perspective distortion makes a 45-degree angle look like a 20-degree angle to the software.
Wow, yeah. If you shoot the video from a high downward angle, it distorts the trunk flexion calculations entirely.
So the software isn't magic, it's a calculator. And the data it spits out is only as good as the safety professional's ability to set up the correct shot and understand the limitations of a 2D sensor.
Right. It validates the need for a broader ergonomics program. The sources emphasize that these rapid assessment tools provide highly useful quantitative baseline numbers, often expressed as percentages of the video where the worker is in a risky posture, but they rely on worksite analysis in employee involvement.
Yes. RULA and REBA evaluate posture, repetition, and generalized load, but they do not calculate the actual internal forces acting on the spine when you lift something heavy.
Which forms the perfect bridge to our final quantitative tool for this session. Because if I am holding a 2-pound feather versus a 50-pound iron anvil in the exact same awkward posture, my REBA score might look somewhat similar because the posture is identical, but the actual catastrophic risk to my lower back is vastly different.
Oh, vastly.
So how do we account for the raw physics of heavy lifting? We briefly pivot to the NIOSH lifting equation.
Right. And as we mentioned, setting the boundary, this is a massive topic. We're just touching on its core mechanics today to round out the ASP Domain 3 Topic 7 requirements.
Exactly. So let's define the primary target of the equation, the RWL.
RWL stands for Recommended Weight Limit. The biomechanical foundation of the IOSH equation is based on the compressive forces acting on the L5-S1 vertebral disc in the lower back.
That's right at the base of the spine.
Right. Research indicates that when compressive forces on that specific disc exceed 3,400 newtons, the microfractures in the cartilage begin, and the risk of a severe lower back injury skyrockets.
So the equation calculates how to avoid hitting 3,400 newtons.
Precisely. The definition of the RWL is the specific weight of a load that nearly all healthy workers can lift over a substantial period up to 8 hours without an increased risk of developing lifting-related low back pain.
And the baseline constant for the RWL under absolutely perfect, idealized lifting conditions, meaning the box is right against your stomach at waist height with no twisting, lifted exactly once, is 51 pounds.
Right. But every time the task deviates from perfect, if you have to reach forward, if you have to twist, if you have to lift it from the floor, one of the NIOSH multipliers acts as a penalty fraction. It drags that 51-pound limit down until you arrive at the specific RWL for that exact job.
But how does a safety professional use the RWL in the field to assess actual risk? Knowing the safe limit is 20 pounds doesn't tell you the actual risk until you compare it to what the worker is actually lifting.
And that comparison is the final metric, the lifting index, or LI.
The LI. So what is the equation for that?
The equation is incredibly straightforward. LI equals the actual load weight divided by the calculated recommended weight limit. LI equals LW over RWL.
So let's pull the exact concrete example from the CSP practice question bank in our sources. If a warehouse task has an actual load weight of 70 pounds and the safety professional calculates the RWL for this awkward configuration is only 20 pounds, what is the lifting index?
You take the actual load of 70 pounds, divide it by the recommended limit of 20 pounds, and you get a lifting index of 3.5.
So 3.5. This raises an important question, right? What does a 3.5 actually mean for the physical reality of the worker?
Well, any lifting index over 1.0 indicates that the task poses an increased risk of injury. An LI of 1.0 means the actual weight perfectly matches the recommended weight.
Okay, so 1.0 is the threshold.
Right. As the index climbs, the risk multiplies. An LI of greater than 3.0 is generally considered a severe hazard that exceeds the physical capabilities of nearly the entire workforce.
Wow. So a 3.5 represents a severe mismatch between the person and the task.
A 3.5 is not a scenario where you tell the worker to lift with their legs or give them a back belt. A 3.5 means we are entering the territory of tearing ligaments, rupturing discs, and causing permanent damage. It requires immediate ergonomic intervention.
Like moving the origin and destination points closer together or raising the height at the origin?
Exactly. When you see a 3.5, you use the NIOSH equation in reverse to fix it. You look at your multipliers to see what penalized the score the most. Is the horizontal multiplier dragging the RWL down because they're reaching 25 inches away? You redesign the conveyor belt to bring the box within 10 inches.
By decreasing the horizontal reach, the RWL mathematically increases, which drops the overall lifting index below 1.0.
You identify the risk mathematically, and you eliminate it structurally.
This has been a massive journey through the entire landscape of ergonomic assessment. We've moved from the initial triage of qualitative checklists to the absolute precision of quantitative tools.
We've mapped static and dynamic anthropometry, quantified joint movement with Goniometers, scaled our capabilities with RULA and REBA software, and calculated the hard limits of lifting with the NIOSH equation.
So what does this all mean for you as you prepare for the exam? It means that passing the ASP exam requires knowing that ergonomic safety is no longer a guessing game. It is a measurable, systematic science of adapting the job to the worker.
It is. And as we close, I want to leave you with a final thought to ponder. As software programs for RULA and REBA become incredibly advanced at identifying risk from just a few seconds of video, we must be careful not to lose the human element.
Oh, that's a great point. Imagine this scenario. You record a worker, run the video through the software, and the algorithm tells you the posture is perfectly safe. It gives you a RULA score of 2, a bright green light.
Right. But when you look at your qualitative symptom survey, That exact same worker is reporting chronic, severe pain in their shoulder every single day.
If the algorithmic quantitative data says everything is fine and the qualitative human experience says it hurts, which data point do you trust?
Algorithms lack context, right? A 2D camera doesn't know about microscopic tendon friction or psychosocial stressors. The true mastery of ergonomics might lie in what happens when the quantitative data and the qualitative human experience contradict each other.
You cannot automate empathy. The human being is always the final metric. Thank you for joining this session of QHSE Talks. Keep studying, keep measuring, and most importantly, keep adapting the world to the worker. We will see you next time.